this video, we'll give a few examples where we apply the alternating series test to tell whether or not an alternating series converges or diverges. I'll start by giving a slightly different version of the test than we did in the first video. So suppose you have an alternating series. It looks like -1 to the n times bn or -1 to the n plus 1 times bn. Either one is okay. The bn's are positive, and this -1 term is saying that our terms flip back and forth, positive, negative, positive, negative, or negative, positive, negative, positive. And this satisfies that bn is bigger than bn plus 1. It doesn't have to be true for all n, but it has to be true for all sufficiently large n. That means it's okay that this bn sequence might not be decreasing the whole way. Maybe b1 to b2 increases a little bit, and then increases a little to b3, and increases a little to b4, but then after n equals 4, it's always decreasing. That's still okay. So it doesn't matter what happens at the very, very beginning of your sequence. You just need it to be true that for all sufficiently large n, your sequence is decreasing. And it still needs to be true that the limit as n goes to infinity of bn is 0. Then your series converges. Okay, so here's an example. A sum from n equals 1 to infinity of cosine pi n plus 1 times n squared over n cubed plus 1. Okay, so the first thing to try to understand is, like, even is this an alternating series? So what does cosine pi n look like? Well, oh, this should be a capital N. What does cosine pi n look like? I mean, cosine of pi is -1. And cosine of 2 pi is 1. And cosine of 3 pi is -1. And cosine of 4 pi is 1. Cosine of pi n is equal to -1 to the n. These are just a different way of writing the same function. And the reason that I've written it this way is for problems that are, like, intended to be tricky. This is just another way to rewrite the function -1 to the n. And this is forcing you to recognize this. But okay, I see this function cosine pi n plus 1. I'm just going to replace it with -1 to the n plus 1. Okay, so we have -1 to the n plus 1 times n squared over n cubed plus 1. And what do we need to check? This n cubed, this n squared over n cubed plus 1, this is our bn. So the important thing is to show two properties, n squared over n cubed plus 1. We need to show that this is decreasing, not necessarily for all n, but for all sufficiently large n. So for n large enough. And then we have to show that the limit as n goes to infinity of n squared over n cubed plus 1 equals 0. And you can already see why this is true, but I'm going to pause and erase, and I'll do the details of checking these two properties here. Let's check these two properties that we need in order to apply the alternating series test. And let's do the second one first and see why the limit as n goes to infinity of n squared over n cubed plus 1 equals 0. Well, what's the general idea in working with a sequence like this? Is we factor out the highest power of n from the numerator and the denominator. That gives us n squared over n cubed times 1 over 1 plus 1 over n cubed. And the point is that this 1 over 1 plus 1 over n cubed is 1 over 1 plus something that's going to go to 0 as n goes to infinity. This n squared cancels with this n here. And we can see that the limit as n goes to infinity is something going to 0 times something going to 1 over 1 plus 0. So we get 0. The trickier part, and this is often, I mean almost always the trickier part in dealing with alternating series, is showing that your series is decreasing for n large enough. How do you show a function is decreasing? Is with the first derivative test. So let's define a function f of x so that f of capital N is equal to bn. Okay, and now the idea is to apply the first derivative test. So what is the derivative? Well, we'll use the quotient rule. It's ho d high minus high d ho over ho ho. That's just how I remember it. It's a little embarrassing to say, but it'll stick. It's like a Snow White and the Seven Dwarfs type of thing, like hi d ho. Yeah. Okay. So x cubed plus 1, d high is 2x minus high d ho, 3x squared over ho ho, x cubed plus 1 squared. So let me rewrite this less cramped over here. So we get 2x to the 5th, x cubed times, sorry, 2x to the 4th, x cubed times 2x, 2x to the 4th, plus 2x minus 3x to the 4th, 3x to the 4th, over whatever the denominator is, x cubed plus 1 squared. And the numerator now is minus x to the 4th plus 2x. And we can factor that even a little more. We get minus x cubed plus 2 times x over the denominator. So why am I not expanding the denominator or anything? Is that I don't really care what the denominator is. I just want to tell whether or not this function is positive or negative. And the denominator is a square. So it's always going to be positive. It's the square of something that's not 0. So f prime of x is less than or equal to 0 as long as the numerator is less than or equal to 0. So let me say if, but really if and only if, minus x cubed minus 2 times x is less than or equal to 0. And we only really care about showing that this is decreasing once n is large enough. So you can think of x as being a positive number. So the x part is positive. This minus 1 part is negative. So this is definitely true if x cubed is greater than 2, so that this part is positive, which is true if x is greater than, well, let me say greater than or equal to the cube root of 2. So note, this does not tell us that this sequence is decreasing when you go from n equals 1 to n equals 2, because the function is not decreasing on that whole interval. But it does say that as soon as x is bigger than cube root of 2, this function is decreasing. So similarly, for values of n bigger than cube root of 2, the sequence will also be decreasing. So what have we checked? We've checked that this series that we started with, this series here, it's minus 1 to a power times, so this got a little smudged. It's minus 1 to a power times this bn, n squared over n cubed plus 1. And this bn sequence is decreasing for n large enough. Here, that's going to be for all n that are at least like 2, because then you're from 2 to 3, you're entirely in this interval where this function is decreasing. So it is decreasing, and the limit, it is decreasing for n large enough, and the limit of these bn's is 0. So this converges by AST. So the alternating series test is as simple to apply as it is to check that a sequence is decreasing and that a sequence is going to 0. So I'm going to pause and erase, and then we'll do our next example. Let's look at our next series, the sum from n equals 0 to infinity of minus 1 to the n times 3n over 4n minus 1. And let me point out the first thing. This starts at n equals 0 instead of n equals 1. But when you put in n equals 0, what do you get? Minus 1 to the 0 is 1, times 3 times 0 over 4 times 0 minus 1. The 3 times 0 gives you 0 here. So this is the same thing as a sum from n equals 1 to infinity of minus 1 to the n times 3n over 4n minus 1. So this starting at n equals 0 versus starting at n equals 1 is not a real problem. You might initially think like, oh, this starts at n equals 0. I can't apply the alternating series test. But you always can. You can just put in the value, see what you get, and then the rest of the series, you'll get some number plus some series that you can try to apply the alternating series test to. Okay, so that's not a real problem. Okay, so here's our Bn. And we want to check, is Bn decreasing? So what does it look like? Well, when n is 1, what we get is 3 over 3 times 1 minus 1 is 3. We get 1. And then we get 6 over 7. And then we get 9 over 11. So maybe it's not totally clear one way or the other, but it looks like it's decreasing at the beginning. Let's let f of x be 3x, 4x minus 1. It's okay. F prime of x. I mean, it looks like this should be decreasing because every time you increase n, the numerator is going up by 3, and the denominator is growing faster. It's going up by 4. But let's really check. So 4x minus 1 times 3 minus high d ho 3x times 4 over 4x minus 1 squared, which is the same as 12x minus 3x minus 12x over 4x minus 1 squared. These 12x's cancel. You just get 3x negative over 4x minus 1 squared. So this is less than or equal to 0 for all x bigger than 0. So this Bn sequence is decreasing because this function Fn is decreasing. Okay, so let's do the next part. What is the limit as n goes to infinity of Bn? It's equal to the limit as n goes to infinity of 3n over 4n minus 1. And if you want to be really careful here, you can do this thing where you factor out the highest power of n from the numerator and the denominator. You get n over n times 3 over 4 minus 1 over n. So we get something going to 1 times something going to 3 over 4 minus 0. And that's going to 3/4, which is not 0, not equal to 0. So this is just like in the last example of the last video. You have to be a little careful. The alternating series test doesn't say anything because the limit as n goes to infinity of Bn is not 0. So you can't apply alternating series test because the limit is not 0. And if you take a step back and you think, okay, well, what can I do with this series? The reason that you can't apply the alternating series test is that the limit of these Bn's is not 0, which means the limit of minus 1 to the n times Bn is also not 0. So this diverges by the divergence test, something way easier. So when you see an alternating series, your feeling might be like, let me just apply the alternating series test right away. And the first thing that you might do is do this part to check that Bn is decreasing. But then when you do the next part, you'll realize that, in fact, you could have skipped a bunch of work at the beginning by just applying the divergence test to see that this series diverges. So I'll pause and erase, and we'll do one final example in this video. For our final example, let's look at this series, a sum from n equals 1 to infinity of minus 1 to the n times sine of 1 over n. So this is closely related to the series that we saw last time when we talked about the limit comparison test, except we talked about the series where we don't have this minus 1 over n. So sine of 1 over n is going to be our Bn. Okay, so is it true that Bn is decreasing? Well, let's let f of x be equal to sine of 1 over x. We can apply the first derivative test, but before we do, let's just see what do we expect. When n is getting bigger, we're taking sine of smaller and smaller numbers, and sine of angles close to 0 are getting close to 0. So this should be decreasing. I mean, just intuitively when you think about it, but we can really check this way. f prime of x is cosine of 1 over x times minus 1 over x squared. This is negative, and this is positive. Right, as soon as x is positive. So this is going to be decreasing. So Bn is decreasing. Now we just have to check what is the limit as n goes to infinity of Bn. Well, this is a limit as n goes to infinity of sine of 1 over n, which is the limit as x goes to 0 from the plus direction of sine of x, right? Because we're taking smaller and smaller and smaller. 1 over n is smaller and smaller and smaller from the plus direction as n goes to infinity. So this really is sine of 0, which is 0. So we apply the alternating series test and see that this series S converges by the alternating series test. So this is an example of a series that maybe looks complicated at the beginning. Remember, telling whether or not this series without the minus 1 to the n converged or diverged was pretty tricky. But when you put in this minus 1 to the n, it's pretty straightforward to apply this test and see that the series converges.